So in the last hour, I asked you to calculate force on the particle of mass m due to a sphere having cavity. So I said this sphere has mass m and radius r. Now we have removed this much portion of the sphere. Then what is the net force on this small m is a question. Then as usual, to find out the total force on this small m, our normal method is force is equal to force due to complete sphere, means complete means as if there is no cavity, minus force on this small m due to cavity. Then if I analyze this sphere, then the complete mass of this sphere is assumed to be concentrated here. Okay, that I'll call it as capital E. And the mass of this cavity is assumed to be concentrated here. This I'll call it as m dash. Then this is a small m. If you look at the distance from here to here, distance is r, this is r, 2r. Therefore I can say here to here distance is 2r. And distance from center of cavity to this small m is, see, it is r plus r by 2. You know r plus r by 2 is 3r by 2. You can calculate here r plus r by 2. LCM is 2. It's 2 plus 1 is 3. 3r by 2. So from here to here is 3r by 2. 3r by 2. Then we have to calculate the force. See here, to write the force, I can say capital E. We can write like this: F is equal to capital G, and complete mass is capital M into small m divided by distance square, r and r, 2r whole square is 4r square, minus, due to cavity is capital G, mass of the cavity is m dash into small m divided by this distance is 3r by 2 whole square. If I write directly, it is 4 by 9r square. And we can take, or otherwise here capital M is given, small m is given, capital G is known, r is known. Here also capital G, small m, r is known, but only unknown is m dash. Means we have to calculate m dash. M dash means mass of the cavity. So to find out the mass of the cavity, I told in the previous topics, we have to use a density concept. Here, since it is a sphere, I can say volume density. You can represent by, in letter I can use rho is equal to total mass divided by total volume, 4 by 3 pi r cube is equal to, for density of the cavity is m dash divided by volume is 4 by 3 pi radius of the cavity cube, means r cube divided by 9. Sorry, this r by 2 means it's a 4. R by 2 cube. 2 cube is 8. 2 cube is 8. Then see, if I compare these two, 4 by 3 pi, 4 by 3 pi get cancels. Then r cube get cancelled. Then we can write capital M is equal to, or otherwise I'll try to write here, that implies capital M is equal to, this is m dash whole divided by 1 by 8. Instead of 1 whole divided by, I can write 8 m dash, or m dash can be written as m by 8. Then if I substitute capital G, F is equal to, in both terms, capital G, small m, and r square are common. Then what is remains in the first, here first I will write the common things, capital G, small m divided by r square is common. In bracket, the remaining is m by 4. Here in first term we left with m by 4 minus 4 m dash divided by 9. Here capital G, small m by r square in bracket m by 4 minus 4 by 9. Here m dash means I can say m divided by 8. M divided by 8. Here 2 2s are 2 4s are. Now in these two terms, m by 4 I can take common. Then capital G, capital M, small m by 4 r square. Okay. Then what is left here? 1 minus, in numerator it is 2, in the denominator it is 9. Then what is LCM? 9. 9 minus 2 is 7. So final answer is F is equal to 7 by 9 for this bracket. Then capital G, capital M, small m divided by 4 r square. Or otherwise you can multiply 4 and 9. Capital G, capital M, small m by 36 r square. So this is the force on small m due to a sphere having cavity. Okay. So this is our yesterday's homework problem. Please you can copy. Okay, next kind of problems on this Newton's law of gravitation is zero force. But zero force or null point we can discuss in electric field concept. Now the next heading is acceleration due to gravity. Acceleration due to gravity. Acceleration due to gravity, or it is also called as gravitational field intensity. Gravitational field or gravitational field intensity, both are same only, right? Here in this heading we discuss acceleration due to gravity as well as variation of acceleration due to gravity with height, depth as well as rotation. Okay, now as you know, consider a planet of mass m and radius r. Then in our theory we derived the relation between capital G and small g, that is small g is equal to capital G capital M by r square, where capital G means universal gravitational constant, M means mass of the planet whose acceleration due to gravity is calculated, r is the radius of the planet. While deriving this expression we assume that Earth is a perfect sphere of uniform density. If you consider Earth shape of the Earth is not a perfect sphere and density of Earth is not uniform from center to the surface. Even though for our convenience we assume density is uniform and shape is a sphere. Okay, then it is an expression. Now this is in terms of mass. We can also write in terms of density also, because we assume density of the Earth is constant. That is, density is equal to mass divided by volume, or mass can be written as density into volume, or density into volume means 4 by 3 pi r cube. If you substitute this m here, then capital G is equal to, small g is equal to capital G divided by r square. Instead of small m I can write 4 by 3 pi r cube into density. Here this r square and this r cube get cancels, only r is left here. Then G can be written as 4 by 3 pi G rho r. This is also the expression for acceleration due to gravity in terms of density. It is expression for acceleration due to gravity in terms of mass. Okay, now here most of the times we come across questions on percentage change in G. Here sometimes, as you know, if mass increases, G also increases. If a radius increases, G decreases. That we know. Okay, see here. If there is only change in mass, only change in mass, only change in mass, I'm talking only small change in mass, small change in mass, then percentage change in G is percentage change delta G by G. You can multiply by 100 also. Okay, so percentage change in G is equal to delta M by M. Is a fractional change. If you multiply by 100 on both sides, you get percentage change. and if there is only change in radius, only change in radius, only change in radius. That is once again only for small change in radius. Fractional change in g. If you multiply by 100, you get percentage change. So always, as I told you earlier, to find out the percentage change or fractional change, we have to take power into fractional change. That is a change. Power into change. Here for radius, power is 2. Therefore, 2 into delta r by r. Multiplied by 100, you can get percentage change. If there is small change in both, small change in both m and r, then capital G, change in acceleration due to gravity is equal to delta m by m. Since it is as mass increases, G also increases. That's why we used to take plus. But as radius increases, G decreases. That is, G and R inversely proportional. Hence, we have to take minus 2 into delta R by R. So, in my opinion, this is a very important relation. In every book you find questions on this. Okay, if you know, you can solve any kind of questions, right? So pause the screen and calculate. Okay, let's have some questions on calculation of G. First, I'll start from this. There's a very common question in our CET books, that is, if the radius of the earth shrink by 1%, shrink means decrease by 1%, then what is the percentage change in G is how much? Percentage change in G is how much? So, but mass remains same, m remains same. Here delta R percent is equal to 1% and m remains same. Then percentage change in G. As you know, if m remains same means percentage or change in m is 0, 0 by anything is 0. Minus indicates the G and R are inversely proportional. Here I said shrink means decrease. If R decreases, G increases. Therefore, 2 into percentage change in GR is 1%. Here it is 1%. Therefore, percentage change in G is equal to 2 into 1% is 2%. This is a very common question in our CET books. Okay, so pause the screen and calculate. Next question. If we have a planet, whose mass and radius is half of the mass and radius of the Earth, that is, mass of the planet is equal to mass of the earth by 2 and radius of the planet is equal to radius of earth by 2. Then acceleration due to gravity of the planet is how many times of acceleration due to gravity of the earth. Okay, or they can ask the ratio concept. Okay, answer is simple. Say acceleration due to gravity of the earth is written as capital G capital M of the earth divided by radius of the earth whole square. Okay, similarly acceleration due to gravity of the planet is equal to capital G as it is mass of the earth. Here I have to write mass of the planet divided by radius of the planet whole square. Then G of the planet is equal to capital G as it is mass of the planet is equal to mass of the earth by 2 and radius of the planet is equal to radius of the earth by 2. If I make it a square, directly I will try to write 4 by radius of the earth whole square. You know, capital G M E by R E square is nothing but acceleration due to gravity of the earth. Okay, then it's a 2 1s, it's 2 2s. Then finally I can write acceleration due to gravity of the planet is equal to 2 times of acceleration due to gravity of the earth. Okay, copy this. Next, question. If weight of a person on earth is equal to say 600 Newton and acceleration due to gravity on the earth is 10 meter per second square and acceleration due to gravity on moon is 1 by 6 times of acceleration due to gravity of the earth, then what is the weight of the same person on moon is how much? Pause the screen and calculate. Okay, come on. See, weight is equal to M into G. You know, mass remains same on earth as well as on moon. Hence, weight is directly proportional to G. Weight is directly proportional to G. If G on moon is 1 by 6 times of the earth means weight is also 1 by 6 times of that of the earth. Hence, you can substitute and simplify. Your answer will be 100 Newton. Please try yourself. Okay, so I'll give you 2 more questions for your homework. Practice, they are easy. Answers will be given in the next hour. Here I have some questions. If G on moon by G on earth is 1 by 6 and density of earth divided by density of moon is 5/3. Then what is the ratio of radius of moon to the radius of earth? First question. And next is, if diameter of one planet divided by diameter of second planet is 4/1 and density of first planet to the density of second planet is 1/2, then what is the ratio of acceleration due to gravity of first planet to the second planet? Okay, so practice these two questions. We'll meet in the next hour.